We now want to address in section 19.2 some mathematical aspects of the first law. Now, what is this first law? The first law is that the change in the internal energy is going to be equal to the change in the heat that's put into the system minus the change in the work that is done on the exterior, that's out of the system. So this change in energy is naturally going to be this. It's into an intuition that the energy that comes in minus the energy that goes out. And we do this in the form of heat coming in and work going out for the reasons I just explained in the last section. Now, how do we determine what this work is? Well, the work differs depending upon the type of process we have. Isobaric, isothermal, isochoric, or adiabatic. And now we have to look at how that change takes place. First of all, let's look at, and I've explained it again here in the form of originating in the form of a steam engine. Let's look at an isobaric process. Isobaric process means that there's no change in the pressure. Now, if there's no change in the pressure, it can be shown that the change in the work is equal to the pressure times the change in the volume. And the reason for this is the pressure, you recall, is really the force per unit area. So if I think about this as being a force per unit area, and I think about work as being, I think about the volume as being area times the distance that I go, then you could say, oh, that makes sense because the areas cancel and work is force times distance. Conversely, I could say, I could begin with, well, work is force times distance in the direction of motion. And I could multiply by an area and divide by an area. Then I would get the pressure times the volume, the change in the volume. So the change in the volume, if the area is constant, like with a piston, the piston moves, let's take a circular piston here. As the piston moves inside a cylinder, then of course the change in it has a constant area and you have a change in x going in the direction that it's moving. So for an isobaric process, that means the pressure is constant. That means basically that the force is constant. So it's just basically going to be force times distance. So if I look at that over a period of time, I don't have to worry about the pressure changing. It's only the change in the volume. The next one is isothermal. And for an isothermal process, it's a little bit more complex because we have to look at the interplay of the changing pressure and the changing volume. So here we have, with isothermal, the change in temperature is equal to 0. Well, what happens to the work then? Well, it can be proved, and we're not going to prove that at this point in this course. So simply take it from me that the change in the work is N, that's the number of moles, times the gas constant, times the temperature, remember it's a constant, times the natural log of the volume finally divided by the volume initially. Now you may recall that that's actually going to end up being the ratio of those two as logs becomes their quotient. So if we have any process where I go from an initial volume to a final volume, when the temperature is constant, then it turns out that this is the amount of work we're doing if we have an ideal gas. Okay, that's isothermal. What about adiabatic? And I will not prove this either, but if we have an adiabatic process, in other words, there's no heat change, then the amount of work that's done in this process is 3/2 nR T initial minus T final. So the temperature can change, but there's no heat exchanged, and the volume and the pressure may change, but there's no change overall in the amount of heat that is in the system. And this is how much work is done. How can work be done? Well, you can have the system where the piston expands and the temperature is lowered And so the temperature finally is going to be cooler than the temperature initially, which is the reason why you're right, T initial minus T final here. Now that's for N moles of a monoatomic gas. If you have an adiabatic ideal gas, then you can show adiabatic ideal gas. There's a relationship that can be proven where PV to the power gamma initially is equal to PV final to the power gamma, where gamma is equal to Cp divided by Cv. And we have discussed Cp and Cv before, being at constant pressure and at constant volume, the specific heats. And this, again, all three of these, I'm not going to prove at this point in the course, but you simply have to know these in order to compute the work that's done in these three different circumstances. And remember, this was very important during the 1800s as people looked at steam engines. Now, of course, we're looking at equivalent types of things. We're looking at generating electricity. And in generating electricity, we're doing exactly the same thing with turbines and with using coal and nuclear power and other types of fossil fuels, such as not only coal, but natural gas and even gasoline in some cases to generate electricity, plus, of course, being able to generate heat from nuclear processes such as nuclear fission. In the next section, we'll be talking about specific heats some more, but these are the ratios of the two specific heats that give you gamma, and we'll discuss gamma this a little bit more when we talk more about ideal gases.